think
not
we should
as easy as the previous exam you gave us. Start for order 2 degree, just like this. It was easier questions from the work. So you need to use art integration, stuff like that, add the
I know you know
yeah,
that.
stuff like that, yeah, integration of art and stuff like that. I can hope to get something as
Okay.
easy or the one as this.
Okay, normally, try to make some, we get it to something more easier. Because this is a finite element piece, again, it's not this one.
Thank you,
It's
sir.
not the main topic of this course. Normally, you should be familiar and comfortable with this at this stage. As you have the courses on finite elements. But okay, well, if I look at the history of exams, I pick a case which is already discrete. There is only 2 hours, so I'm making a longer exam. In 2 hours, it's enough.
Thank you, sir.
So,
I know it's probably not going to be on the exam, but yesterday, just really in general, yesterday when you were doing the porosity, and you were saying, relating to the adiabatic case, if you keep the porosity constant, well, temperature is force-like and porosity is strain-like, right?
Yes.
Temperature or pressure are force-like, right?
yes.
And porosity, and what was the other one? Is strain-like?
Entropy.
Entropy, okay.
So that's one thing I wanted to look at here. I wanted to do this. I can do tomorrow if I have the time to do it.
For the example that you did, that you gave us for the review, this is a really dumb question, but does it matter what side the n equation or the n+1 terms are? Does it matter if it's on the left or the right side? Or is it generally the n+1 has to be on the left side when you put the matrix?
Okay, so let's try to do this so that everybody can the question. So yeah, you just isolate the n and n+1 in different parts. Okay, since we are Western European tradition, we put on the left the result and on the right the input.
So
Maybe you can either read left to right, right to left.
So left side has to be n+1 because it's the.
Yeah, but it's just convention. Yes.
Sure.
The point is that you isolate the n+1 in the n in different sides.
They just have to be on different
There's the
sides.
thing which
but
is known.
generally
Input
n+1.
output.
Yeah.
You can put it one on the right, one on the left if you want.
Okay. Can you go over again?
Okay. Well, you look, I don't know how you want to organize the questions with the Chevron list. What?
I didn't understand what you're saying.
Okay, she was asking about the n+1 and when you do the time discretization. About does it have a meaning, special meaning to put things on the right or on the left? It's not especially right and left. I mean, you want to isolate what is known and what is unknown. If you want to write the equation, read the equation from left to right or from right to left, it's up to you. But, the mathematical convention is that you put the unknowns on the left and the unknown on the right. That's okay. Just
Professor, sorry, I was absent last week. In this
Monday, yes, yeah.
So I was wondering, so the exam would be similar to the exercise you gave us?
Yes.
Okay.
The exercise is actually, okay, this exercise is, was one of the,
Was the previous one?
it's a previous one, and okay, it's one bit more complicated than that.
Okay.
You can consider this as a,
So that one is more complicated because it took me 4 hours to finish.
yes.
Oh, this, yeah. Oh, God.
Yeah.
Okay. Okay, this was a training, okay, normally you can train to the exam also, so, but,
I would be trained for 3 hours. Not 2.
no, but
It
okay.
will be similar but easy version.
Okay,
It won't be.
it won't be harder, okay?
Okay.
From my point of view, again, it won't be harder, but okay, I mean,
So always from an exercise and then develop it by question and answers.
okay, so this belongs to another version of the course, but, so I may add a few more theoretical questions or general questions, but not deriving
So not demonstration.
not a demonstration, but more questions about your understanding of some principles,
Okay.
some general
So
things,
some theory.
some theory, but not going into the details. Just
Okay.
trying to see if you have a sense
Of the course.
of the course of what is a good practice, bad practice. I mean, it's a little bit the variance on the last question. So the last question is very often not done so well. It looks simple.
What? Sorry.
It's the last question of the last question of the
Okay,
sample.
Okay.
Where I ask, okay, put the advantages and the drawbacks of each method. And I asked to illustrate this on the example which was just done before. Most students, they just give back the few sentences I did in the slides.
Mm.
Okay, but that's not what I'm asking. I want to like you to comment on the example. Okay.
Of course, this is an example. Yeah.
So the ideally everything is connected and it makes reference to each other in the sense of.
So except for that, do you have any other suggestion, like studying the mesh or something else to revise more?
No, you can redo the derivation of the. If you have done the theory of your, if you know well the theory of your exercise, coding exercise, understand it well. Okay, because it's always, if you look, I mean, okay, maybe for you it's not obvious on first sight, but okay, it's always the same exercise. Just the equations change, but the logic is, it's not a recipe, but okay, it's just the logic of steps to do. Okay, you write the equations, you put them in first order, you check stability, just to make sure that it's fine. And then you derive a monolithic approach, and then from a monolithic time discrete, and then you just think of staggered approaches. And you can expect that I'm going to ask something like this. This is the heart of the course. Okay? Now in this course there are a few more things about variational approaches and things like this. So there may be a few extra questions, but okay, again, in the 2 hours, it's not easy to do much more than this part on the staggered and everything. So I focus on that typically. You can expect that the exam will focus on that, plus maybe a few questions from on theoretical or on the general understanding questions of the theory. Questions where you can answer by sentences, not math.
Open questions.
Open questions.
Okay. So last thing, sorry, I heard about a sheet paper.
Yes.
We're allowed to.
Okay, so you are allowed to bring a cheat sheet if you want. So one page.
Only one page.
Front and
It's a
back.
1 page.
That's not enough.
Front and back.
This part of the exercise is
You
fine.
said front and back. one
Yeah,
page.
two sides.
And then 2 page.
No, okay, so I want one sheet of paper, A4.
So one and behind.
Yes. So okay, I want it basically handwritten. In the sense I don't want the typeset version. Otherwise, I mean, somebody's going to one person is going to do it, and everybody's going to use the same. And I think I'm convinced that writing this sheet is part of your learning of studying for the exam. Choosing what you put there, what you don't put there. It's an exercise in itself.
Expect us to write at a very small.
No, yeah, no,
Expect that.
no magnifying glass allowed.
No magnet.
No magnifying
Can I
glass.
ask a real question?
Nobody think.
Well,
Speak,
Oh, why? Why not? I was expecting to come with my answer.
the microphone. Okay, so
Can
Right,
we use
one and a half
the
reason.
A0?
no,
Let's say do
more.
out my
A0. A0 is 24 times easy.
Okay, actual question. Between the, question number 3 and question number 4,
Yes.
is when you're asking about like the staggered approach to solve the problem versus a system of equations, when do you actually put it in the matrix? Like you write the system equation, do you put it in the matrix when you actually ask about a staggered approach? I just want to make sure I'm putting the right thing for each problem.
Okay, so when you have the monolithic the time discretization, it's convenient to write it in the matrix form because
Yes.
that's how you solve it. Okay, so then the staggered approach. Normally you solve two problems, okay? Two sub-problems. Each sub-problem can be written in the matrix form.
Yeah.
Then there is, most of the time, there is the option to merge the two systems into one singular, one unique matrix form, okay?
Yeah.
Which is, convenient in terms of studying the properties of the algorithm, which is, in a real case, in a real life, you will never do that because you don't want to assemble. The point of doing the staggered is just not to assemble these big matrices.
Yeah.
So, I mean, this is more to analyze things. So it's not mandatory to write it in a single matrix form for the.
System of equations.
From another thing.
Because, I'm just thinking about how we solve the practice problems. So for question 3, it's like write the system of equations corresponding to the monolithic approach. So if you write all the stuff, you write all your equations
Okay, so
out.
for the monolithic, okay? Monolithic, there's one system. So I want you to write the system of equations, matrix form.
Okay.
Then next, staggered case. The staggered case, okay? Again, so basically it's two systems, two separate set of equations, and each of them you can put them in matrix form. You can then, maybe I should have put an S actually in two systems in that the writing of the question is true. But then you can write the things together into one system. But this is useful to comment on what's happening, show that you have a block, triangular matrix. These are ways to explain why you simplify the problem. Okay? But
Two separate matrices.
it's not mandatory in itself. If you have written properly the two subsystems, for me it's enough. Okay. But then, when you want to comment on the benefits and the drawbacks of each method, the staggered, maybe it's useful to comment on the unified or the integrated matrix.
So is this when I would break it up into the left side and the right
Okay.
side?
I have a question
Yes.
about the question that you gave, the 5-number question from here, you say to limit the stability of the stable approach.
This part?
Limit the stability of the
That's more
Yes,
like
yes.
right?
in here,
No,
you
and
then you separate
deal with
it into
two.
the right hand side and the left hand side involved by whole matrix, the formula you.
Yeah, so this is one reason for which you could
Okay, answer for
in that
this
case,
one that you've done.
to do that, I mean, that if you want to go through
Whatever I've
this
done is really messy and I don't think my
eigenvalues of this amplification matrix, this
See,
algorithmic
explained it before.
matrix,
Yeah, I'm
yes,
gonna
you have
ask
to
this.
put
Like,
it
can
in
you
the-
explain this again?
That's,
So you would have done
I
it-
have pictures, but I didn't.
in the previous question or in that question.
I have a question is like for the staggered, can you do this by the system wise the stability?
But if you can demonstrate that each subsystem is contractive, then it's another way to show that.
Not complex like right hand side and left hand side, just do the system wise, like stage wise separately check the stability, not the whole process, but just like the thing I can take this way, like system wise.
Okay, but in the end, you have a time step and you go from n to n plus 1. Okay, you have an intermediate step. But what do you do with the intermediate values? Okay, it depends on the staggered scheme, of course. In some staggered scheme, the one works only on displacement velocities, for example, and the other one works only on temperature. So maybe but the coupling terms must appear somewhere. And you'll have the initial conditions they are coupling the two systems, so you cannot really do. It doesn't make sense to see the stability of the first set of equation and separately from the second. It's the combination of the two which is the problem. But then, okay, again, if you manage to show that the first step is contractive, second step is contractive,
Oh, separate line to show the contract.
if you change contractive steps, so it's okay. So, but this is a different approach to stability than just looking at the values of the matrix. Yeah, yeah. And then especially because I just was just asking to explain how you would do it, not of course compute the eigenvalues of this matrix. For the,
Can you explain this question again? What you expect? Yeah.
okay, so the okay, so I'm not going to rewrite everything, but okay, what are the ways to compute stability? Okay, so no, but okay, this is a question about the question of stability in the example. Okay, so. Okay, so this is the general way to study stability. If you have an algorithm which you can write in this form, okay. So maybe, okay, of course, this is equivalent to if you have, I keep the notations. Okay, U here, I just put one U, but can be many things. Okay, so of course you can go from here to there quite easily. I use the notations of the monastic case. Okay, so in this case, this means that KH is just this. Okay, so that's why you need to compute this matrix. Okay. And then the stability condition here that the eigenvalues of KH should be less than 1 in the absolute norm. Okay, so. Okay, so KH is a square matrix. Okay, I'm not going to redo the demonstration. Okay, I did it. Okay, I'm not going to ask for the demonstration, but it's into when you change the steps. Okay, you're going to, if you do this, if you replace UN by KH, UN minus 1, and so on, you're going to have powers of KH. Okay, so the amplitude. This matrix proportional to the amplitude of the eigenvalues. So you have the eigenvalues to the power of number of iterations. You know that if something is less than 1, you put it to the power, it will decrease. If ever it's larger than 1, it's going to blow up. Okay, so that's fine. So this is one way. The other way would have been to show that if you are able to show that there is a norm. There is a norm on your system state which is decreasing or non-increasing. Okay, it's the other way, but okay, in this case, I don't even need to talk about time discretization because there's a general theorem which says that if I have this, if I use the beta, okay, the general midpoint, beta larger than 1/2 and the general midpoint, this ensures the stability. Okay? The norm of the distance between U1 and UN plus 1 is going to decrease. The norm between U1 and UN plus 1, the norm of the distance between two different solutions generated from different initial conditions is going to not increase. Okay, but this is usually more difficult to show. So in the exam, I asked you to verify this in the global system, because this was, and I give you the norm, so it's a simple exercise. Okay. Now, so this guarantees the stability of the monolithic foundation, but this doesn't guarantee the stability of the staggered approaches, so that's why you need to do a new check for the staggered case. Okay? So either you are able to show that each of the sub-steps verify this condition, or you have to do this. Okay? Just to vary a little bit exercise, and in this case it's easier to do that. Okay? Also, yes, in this case, this is unconditional stability. In this case, this may be verified if h is not too large, for example, if the time step is not too large. Okay, so this can, even if you don't have unconditional stability, you can still have a stable algorithm, provided you use a small enough time step. That's what happens in the isothermal staggered step. So if you want to have the value of the time step, the critical value of the time step, you need to write this, and then the lambda is going to depend on h, and then you need to find conditions on h such that the lambda is always smaller than 1.
How can it ensure stability of the algorithm and the whole system, but not the same as the staggered approach?
Because you don't solve the exact same problem. It's not the same problem in the end. Because the staggered, you don't verify the same equations in the end. So, but the equations you solve in the staggered scheme are not the same as in the monolithic case. They're close enough, hopefully. And they will be close if you do things right normally. They will be close, as close as you want, provided you use very small time steps. The moment you use larger time steps, they're going to be different. And for large time steps, they may be so different that it becomes unstable. The solution becomes, the difference increases all the time at every iteration.
Professor, in the exercise we did solve physically stable, like the contractivity, the second question. So can't we just apply that here for this thing? You didn't understand what I said.
I'm not sure I understand
Yeah,
the
can I
question.
just have the paper for a second?
The second question, we already say solve that.
So
Yeah.
okay, the second question
Yeah.
is this.
Yeah, we already solved the contractivity here.
Yeah, but this is for the full system of equations.
Yeah.
And this, if you apply the generalized midpoint algorithm to this whole set of equations, which corresponds to the monolithic approach,
Okay, do this for monolithic approach.
this guarantees the monolithic approach.
Okay.
So you don't need to do this. You have you could compute this on the analytic approach, but you already know it's going to be verified. Okay, because by construction, it's not by yeah. This is the power of the demonstration about contractility. Now, if you start to mess around with the equations, you just treat the equations to make it easier to solve numerically. But you don't solve exactly the same problem anymore. You make an extra approximation, and the question is to check that this extra approximation is not ruining the solution. Yes?
When you write contractility and beta is greater than 1/2, in the norm, you don't have a beta?
Yes, this is why. So this you write it in the time continuous regime. Okay? And okay, that's the power again of the demonstration. We did it in the class. Again, I'm not going to ask you to do it again in the exam, but you should remember the results. If my system is contractive, so if I can find the norm
This one is the
of
whole
the state,
system.
okay, which can be a
Instead of life monolithic, this one is staggered.
complex state and composite state and composite distributions, but and this can be if it's continuum mechanics, it's a continuum of field, or it's a continuum integral, if it's a discrete, it just will be a sum. Okay? If I have this, I know that if I use the general midpoint algorithm with a beta larger than 1/2, you have done the demonstration that this means that this norm is going to, even in the time discrete case, the norm of the distance between two state and its perturbation, if you want, will not increase.
Right, so you expand the contractivity to make sure it's true, and then it's true as long, then together with contractivity, as long as you choose a beta greater than 1/2, then you know you have stability.
Yes.
You don't have to verify it's something extra.
Exactly. You have unconditional stability. Stability even for any value of h will be norm will be the distance between the state and its perturbation will be decreasing or not increasing. But of course, the moment you do an arbitrary staggered approach, each of the sub-steps, either you can demonstrate that each of them is contractive, so in one step you just reduce the distance, the next step you reduce the distance again, so all in all you will reduce the distance, so this works. But if you don't have that, and you can, for example, the isothermal staggered approach, you cannot, if you put this in the norm that we used for the monoid case, it won't work. Okay? And so in this case, okay, it doesn't mean it cannot be stable, but you need to check it. In most cases, it will be stable for small enough h. There are a few algorithms which are unconditionally unstable, but normally these are really bad algorithms. So if you do small time steps, I mean the approximation is not too big
For the fourth question, would you have been able to use like the staggered adiabatic, there's this approach for this, or is that not relevant at all in this?
No, you could. I mean, okay, it's not equal adiabatic, but it's probably possible to find an algorithm which is preserving which is equivalent to the adiabatic case. Okay, in that case it was more difficult to make the parallel or the analogy with the thermoelastic case, but for power elasticity, you can make an algorithm where you do one step select constant porosity, and then a step, so you change the displacement, the strain at constant porosity. So the pressure is going to change. There is no transport. Okay. And then the second step where you solve for the transport, the RC part, it fixed deformation of the skeleton. And then this would give you a conditionally stable algorithm.
What do you mean by illustrating your comments in the above system? The last question.
Okay, so that's why I would say, in monolithic case, you have a 3x3 matrix to solve to invert. Okay? In the staggered case, you have a 2x2 matrix and a scalar problem to solve. Okay? So it's cheaper to invert a 2x2 matrix and a scalar than inverting a 3x3 matrix. Okay? So this is an illustration of how you gain. Okay, no, that's what I was saying. No, if you put the staggered form in the staggered scheme in the one single matrix form, okay, then okay, you have to invert 3x3 matrix. But if you know that this matrix is block triangular, you can also reduce the inversion to a simple inverting one 2x2 block and a scalar. Okay, these are very simple examples, of course, where it won't make such a big difference inverting a 2x2 or 3x3 matrix. But even on paper, it's easier to invert a 2x2 matrix than a 3x3. Okay? So there's more chances that you can do it analytically into 2x2 than for a 3x3.
A very silly question, but in the case of the exercise, isn't it technically a 4x4 matrix? No.
Sorry, in that case I was in the terminal
Okay,
case.
okay, fine. Okay.
Yeah, in that case it's you have two 2x2 systems to solve instead of one 4x4. Yeah, that's right. I was stuck on the thermoelastic case. Yeah.
That was wrong.
Yeah, you did.
Okay. Any other questions in a moment? Or
Do we have to know syntax for Python for the exam?
no, I don't need to
Just
ask you
general
coding.
theory.
You've done your part.
Okay.
No.
I was failing.
There's no coding in the exam.
Just understanding the logic.
Okay, yeah, I'm not going to ask you any line of code.
Okay. I just failed.
Just know how to write matrices and stuff. Check what's in here. Okay, so again, try to, okay, if you, so you've done it, but to redo the exercise there, without looking at anything, try to do it from scratch. As if you were in a, even if we've done it, you've probably looked at it, but try to do things without looking at all in your notes, or just using your sheet. Okay, this is something you could try to do. Also, okay, so so you have your sheet. I don't want. Normally, there is no need for calculator or anything, so no phones, no anything. So nowadays, I will ask you to put everybody puts their phone on the desk, shut off or in airplane mode. If I see a phone moving, yeah, I take it. Huh?
No, he's gonna sell them on eBay.
What?
Just in case, just you forget to turn it off.
Yeah, of course, I've written
One more
twice.
week of this. One more week of this.
Well, also, I don't know, my phone is a bit old, I was thinking of turning it.
One more week of not punching people in the face.
At least we don't need I did this example completely. I had a negative sign. I shouldn't.
Check something like this.
And all the night.
I'm not sure for the thermal and the mechanical mesh, like, we're gonna have to know that. Like, for specifically the,
Okay, so
like,
again,
which mesh is better, or.
well, okay, in the, it's not that, I mean, okay, again, it's part, it could be part of the general understanding questions, okay? Not trying you to do demonstrations of that, but okay, if I okay,
Integrate on the
I
front
have to
mesh.
do a transfer between two meshes,
Yeah, the
Yeah.
which
actual.
one should I take? The
Okay.
master mesh and the slave mesh on the other side. Or should I transfer from the coarse mesh be controlled by the fine mesh or the inverse?
Yeah, okay, and not so much the integrating mechanism on each mesh.
No, I think there will be no time for you to ask you these kind of demonstrations.
Yes, yeah.
Thank you. Truly, thank you.
These are my ones.
Truly, thank you. This one. This would be, this would be, this color.
Okay, there's something I'm thinking of this lecture that I was reading, I still don't understand.
I remember I wrote it somewhere.
Oh, I get it.
I remember I wrote this stability somewhere. Okay. What the heck?
Is just generally, is contractivity another way to prove stability, or contractivity and stability exactly the same? Like, is it this a rectangle square thing where a square is a rectangle and contractivity is this type of?
Yeah, the contractivity is a stronger
Okay,
condition.
okay, but not necessarily that stability
It
equals.
could be stable without being contracted. Also, okay, it depends really, well, yeah, most of the time it's just, for sure it could be conditionally stable without being contracted, for example. Definitely.
I was doing this again.
Okay, but, yeah, if your system is not, if you cannot demonstrate it's contractive, you can still demonstrate stability by other ways. This way, but no, if you think about contractivity in terms of thermodynamics, usually it's linked to the dissipative nature of the system. So, okay, for physical system, contractivity normally you can connect it to the second principle of thermodynamics. Things are irreversible because they dissipate, and dissipation is going to dissipate the perturbation, the small differences. Okay, but then if you have a problem with buckling or things like this, but then we enter in an nonlinear range. Okay, then if a system with buckling, with an instability, then what does it mean stability there? The notion of numerical stability has to be redefined somehow.
I had a question, this one is bigger than another. My handwriting is really messy, but this is a stupid question. Does your H term usually go with your n plus beta term, or does it go with the n plus 1 and un term? Does your
No, H is the time step, so it's everywhere.
I think I wrote it to ask, and then when I looked back over my notes, I was like, well, that's stupid. It's everywhere.
It's everywhere.
Just ignore that I
Because,
asked that.
So, okay, so the
No, I got it. Don't.
Don't even try.
the H is going to often come with a beta of 1 minus beta. This is
Yeah.
because the H actually comes from the finite difference approximation of the rates. And you have remultiplied the equation by H. Everything where we have a rate, there is no H.
I didn't multiply that. That was.
And everywhere where you don't have a rate, you have an H. And the generalized Newton method, the terms on the right-hand side of the evolution equation, they are evaluated in n plus beta, so that's why you can get these terms.
I was writing really fast. I think I would get you right down, and I was like, wait, no, you're down.
So, I think I'm going to give you another.
I think it's about something you did yesterday. I know it's not for the exam, but you have, for your third equation, for the constituted equation, we had written it as J equals minus K over viscosity of the fluid times gradient of P. And then down here, when you're doing your generalized standard material stuff, and you rewrite the third equation as del of phi over gradient is P equal. Why doesn't this change? Are you saying that this equation, this different model?
Okay, so this is the way to, okay, so you can write, okay, so come back to this moment. The general, you can write the equations, you can write them directly. Okay. This is my constant equation, the function sigma of epsilon and b. Okay, and I have another constant equation, which is the connection between the flux. And actually, you can also something like this. Get the size correct. Okay, so we write this. Okay, you can maybe, okay, I realize that I need three constant equations, three models, okay? These are models, okay, just okay, so this is the D model. So it says that the change of porosity is linked to the pore pressure and also to the deformation of the bulk, okay? Makes sense? Stress and the flux, okay? So, or there's a simplified version, you postulate the existence, for example, of, okay, I discussed this more to start here, but the function of epsilon and p, to represent the stored energy, and you write it directly, okay? I'm going to write it now, but, so this one, yeah, okay, I'll come back to this one. And the function phi of grad P. Okay, so these are terms, so this is dissipation function of potential. And you can assume, and then you can say that by some thermodynamic reasoning, okay, and here I can write that the flux is equal to okay. So the only difference between this and this is that here I postulate the three equations independently, and here I'm saying okay, the first two they come from one single quantity. Is this, and if I postulate the expression for this, I get the two relations. I need to postulate this one too, I get the third relation, okay? The point of doing that is that if you start, for example, there are, this is useful in thermodynamics, okay, this has to be a convex function of epsilon, it's going to be concave in P, and this one phi has to be convex in grad P, is going to be equivalent to quadratic function of grad P, and this guarantees the stability of the solution. This is linked somehow to the contractility, to the well-posedness of the problem from a thermodynamic point of view, the fact that the solution corresponds to many optimum in the sense it will be well-defined, there will be a well-defined solution, a unique solution, and the dissipation is going to be positive in the second principle of thermodynamics. So if I put some constraint on this, and okay, if I do finite strength, for example, if I assume that this is, can use this as enforce some properties on the stored energy to ensure it's called the rate invariance, the frame invariance, sorry. This guarantees the second principle. Okay, this is a way to add extra conditions which makes things easier afterwards. But okay, again, okay, so here, why the B is the same? If I write maybe I could have used a different tensor here. Okay, in practice it is the same because they come from, there exists, I mean, it wants to say that there exists this stored energy from which I can derive the relations. This is linked to energy, integrating energy from the microscale to the macroscale and stuff like this. This is useful to do thermodynamics and also some analysis of notions of unicity, stability, and stuff like this.
So it's just equivalent, it's not
It's
exactly-
equivalent, it's a
you're not
different way
doing-
to approach the thing.
It's not like we're.
Again, this is stronger assumption than this. But in this case, they are completely equivalent. But here I can choose different functions, which will give me different equations. But here I put more assumptions than here.
Okay.
Okay, so I'm going to have to stop here for today, because as I said, I've got some things at 3. Okay, so tomorrow I'm going to send you the link to Zoom later today. The question is clear. Hopefully there is a working diffusion mailing list for everybody, I hope so. Otherwise I will check that.
I'll disseminate
I
it.
hope I won't have to go get your emails one by one, but okay, I have them somewhere.
If it
Normally
works
there's
for
a
one
list.
person, we'll send it to
There's a
everybody.
predefined list normally, right? But since you have different groups, let me check one thing.
We could have two friends next week. If you could send it to one of us, we could
If
send
you,
it.
yeah, if it gets to one of us, we all end up sending it out to
Okay.
everybody.
Yeah.
So,
No, it's okay, I tried to send it to everybody.
that's fine too.
Please get my email.
My brain is gonna be in shock.
Just missed you out again.
My brain is gonna be in shock until next week, Thursday afternoon.
Machine building? What? Who? What?
She's saying my brain is in shock.